All right, let's move on here in our Module 13 lecture. So here in these next couple examples, we want to use our properties of logarithms to evaluate these different expressions of logs. All right, let's go ahead and take a look at this first example here in example A. It wants us to add together these two logarithms. These are two log base 6 logarithms. And yeah, we can find the sum of logarithms using the product rule. But before we can apply the product rule, we're going to have to get rid of this coefficient. So our first step, we're going to need to apply the power rule. So let's go ahead and use the power rule. And the power rule states the coefficients become the power. So we have log base 6 of 3 to the second power plus log base 6 of 4. As we simplify, we got log base 6 of 9. 3 squared is 9, plus log base 6 of 4. All right, now we can take care of the addition of the logs. So again, we got two log base 6 logs. We've learned that the product rule allows us to add logarithms, right? In our sum of logs, whatever we're taking the log of, right, we're going to multiply that together. So we got log of 9 plus the log of 4. Well, that's going to equal log base 6 of 9 times 4. So there's our product. So applying the product rule. So those two logs become 1. And that gives us log base 6 of 36. And we all know the value of the log. Remember, logs are exponents. So our question is, what power, what exponent do we raise our base to get 36? We know that 6 squared is 36. So again, logs are exponents. So again, it equals 2. So we evaluate that log using our properties of power rule and product rule and our definition of what a log is. All right, let's see if we can find the value of this next example. Now, in this next example, we're dealing with natural logarithms, which are log base e logarithms. All right, and with that said, we could go ahead and do some simplifying here. So remember our property, and we'll write it back up here. We know that log base a of a to the x power always simplifies to x. Well, that's what we have here, right? We know the natural log, and we could if we won't rewrite this. So you can see that. That's log base e of e to the 8th power minus 3 times log base e of e to the 4th power. So we can use our same base rule. So we know this is equal to 8, right? Minus 3 times log base e of e to 4th power, right? We know this is all equal to 4, right? We're using our property there, same base rule. So this is 3 times 4. So we have 8 minus 12, which is negative 4. So natural log of e to the 8th power minus 3 times natural log of e to the 4th power is negative 4. All right, so again, I'm using properties. That one simplified nicely, right? Just using our same base properties. So we reduce those down, right, with our same base rule. All right, so let's move on. Let's use some of our basic properties of logarithms to fill in the missing values to make the following equations true. So in this next example, I've got log base 2 of 7 plus log base 2 of x equal to log base 2 of 35. Well, again, let's think about our property here. So with these being two log base 2 logarithms, and we're adding, right, we can use the product rule. And in the product rule, log of m plus log of n is log of m times n. So that's 7 times x, right, as I use my product rule, right, to combine those, equal to log base 2 of 35. Well, we know now what x would need to be. So what would x have to equal to make that true, right? If log base 2 of 7 times x must equal log base 2 of 35, then 7x is going to have to equal 35. And that means that x, right, would have to equal 5. So again, just using our properties to simplify a little bit, right, we know exactly what we need. Again, those are going to have to be equal if this is going to be equal. All right, let's do the same thing in B. Now in B, I've got a difference of logs with same base, 2 log base e logarithms. So I'm going to use the quotient rule. And the quotient rule says log of m minus log of n is log of m over n. So using the quotient rule, this is the natural log of x divided by 4 equal to the natural log of 3/4. So that implies, right, x, right, it's going to have to equal 3. Right, x over 4 must equal 3 over 4, so 3/4 and 3/4. So we can see our solution in one step, right, using that quotient rule. All right, let's go to our next example. I've got -2 log base 8 of 3 equal to log base 8 of x. Well, let's simplify the left side. So I'm going to go ahead and apply my power rule. So we're using the power rule. Right, what does this simplify to? Right, that coefficient, that factor, becomes the exponent. So it's going to be 3 to the -2 power equal to log base 8 of x. And that's what? Log base 8 of 1 over 3 squared. We know a negative exponent, as we reciprocate, as we flip, that'll change it to a positive. So we'll go ahead and simplify that. And we know that 1 over 3 squared is 1/9 equal to log base 8 of x. So now we know what x needs to equal. So this implies 1/9 must equal x. So there's our value of x. We solve for x using our power rule to help us. All right. All right, moving on. All right, let's talk about solving logarithmic equations. All right, let's go ahead and solve a couple here. And this next example here in G wants to solve for x. Now, there's a couple properties, a couple different rules we're going to think about. Now, log base a of m equal log base a of n implies m equal n. Log base a of x equal y implies a to y equal x. Sometimes it helps us to rewrite it exponentially to solve it. Sometimes we can do it just using the same basis. Let's take this first example. Natural log of 12 minus natural log of x plus 1 equal natural log of 4 wants to solve the equation, wants to know what x equals. Well, I'm going to go ahead and apply the quotient rule. Choose the quotient rule first. So that's going to be natural log of 12 divided by x plus 1 equal to the natural log of 4. Well, that implies, since both sides are log base e, that implies 12 over x plus 1 equal 4. So we're just setting up a rational equation to go solve, which we all know how to solve a rational. Right? We can go ahead and clear the fraction. We can multiply both sides by the LCD. So that implies 12 equals 4 times x plus 1, which is 4x plus 4. And then as we solve that for x, right, as we subtract the 4 over, right, we get 8 equal to 4x. And then as we divide out our 4 on both sides, we get our value, our solution of x equal to 2. Right, and you can plug it in and check it. Right, if you would plug 2 back into x, you get natural log of 12 minus the natural log of 2 plus 1, which is 3. And 12 over 3 is 4. So, I mean, it does check. With the check steps, you plug it back in. But again, those had the same bases on both sides, a single log. So I was using this property right here. Log base a of m equal log base a of m implies m equal m. All right, let's look at example B. 2 times log base 7 of x equal log base 7 of 64. Again, question is, what does x equal? So our first step, let's apply the power rule. All right, so using the power rule, this gives us log base 7 of x to the second power equal to log base 7 of 64. Well, again, we can use our same rule. 2 log base 7 logarithms are equal. That implies what we're taking log of must be equal. So x squared must equal 64. And as we solve for x, we can take the square root of both sides. And if you remember, even roots can be positive or negative. So x can equal plus or minus 8. Now, be careful. Here's something we have to talk about. We must check for extraneous solutions. So we've got x equal to 8 or negative 8. Now you remember we cannot take the log of a negative. Extraneous solutions may occur, right? If we were to check, for example, x equal negative 8, what happens? 2 times log base 7 of negative 8. Can't happen. Can't have a negative. Does not check. Now, yeah, you could plug in 8. 8's okay. But that is a extraneous solution. So again, an extra solution we came up with along the way, solution to the quadratic, x squared equals 64, but it's not a solution to the logarithm. So we do have restrictions, right, on our domain, and our domain of logarithm. We remember x, right, must be greater than 0, right? So let's take a look at next example here with C and D. In C, let's see if we can find out what x equals. I've got log base 5 of x equal negative 3. Well, all I can do now is look at rewriting it exponentially. So again, I can't use same base rules like we've been using the other ones, 2 log base 5s, so not log base 5 on the right side. With that said, if I want to know what x is, we're going to convert it, rewrite exponentially using our definition. So remember, log base a of x equal y implies a to the y equal x. So I want to convert it over. So that implies 5 to the negative 3 power must equal x. So log base a of x is y, a to the y is x. So we've gone from here, right, to there. So there's a, right, there's x, there's y. So 5 to the negative 3 power. Well, as we do that, we've got our solution. Of course, 5 to the negative 3 power is 1 over 5 cubed. So x is equal to 1 over 5 times 5 is 25. 25 times 5 is 125. And that checks. You plug it back in. Log base 5 of 125 is negative 3. All right, let's take a look at D. Let's do the same thing on D. Let's see if we can solve this one by looking at it as an exponential. So let's rewrite exponentially. So with that, we've got x, right? Log base a of x is y. Let's rewrite. So that's going to be x to the 1/2 power equal 9. So again, we're converting it, right? So we're going from log base a of x equal y to a to y equal x. And with that, of course, that means we've got the square root of x equal 9. And if we want to solve for x, right, we would square both sides. And we get x equal to 81. And yes, log base 81 of 9 is 1/2, because 81 to 1/2 power is the square root of 81, which is 9. So it does check, right? There's our solution. So rewrite them exponentially. Use your log definition. So again, the log definition, as we talked about, one of the most important things we can talk about. Remember, we're solving these, they come into play. So we'll do a few more here in a little bit. I'm going to stop there with these. We'll continue here in a little bit.